So we talked about groups last time, as we just were mentioning in our quick little review. And so we're going to continue talking about that. But this time we are going to continue talking about the idea of groups, but we're going to be dealing with finite systems. So in case you don't remember what the word finite means that if you're counting, you're going to come to a place where you stop. Okay, it's a set that does not go on forever and ever. So when we talked last time about what the whole numbers were, I used an ellipsis. That made it an infinite set. It's something that never has a place where it stops. So the first example, just to kind of give you a little introduction on how an operation might work in a finite set, we're going to look at a clock. Now I know many of you might not have a clock with dials on it like this. So, but we're still going to use it. We could call this circular arithmetic instead of clock arithmetic to avoid the whole clock issue. But here's what we're going to do. We are going to look at how would I do arithmetic, and in particular addition. How would I do addition in a circular way? Okay, so first off, what we're going to do, if you remember when we were talking about mathematical system, there was two things that we need. We need both a set of objects and we need a binary operation. That was the first definition that's in your notes from last time. So looking at this right here, what are the elements of the set that I am going to use when I'm doing my circular or my clock arithmetic? Perfect, 1 through 12, yes. No tricks, no gimmicks. They're sitting right there in front of you. Okay, so the set of elements are 1 through 12. The binary operation that we are going to be using is addition. And so where we're going to start before we talk about the question of, is this a group, why or why not? Let's just do some examples to familiarize ourselves with how we would do this operation. So for instance, when I am looking at this, let's keep this nice and simple. What if I had 5 plus 4? If you're looking at the clock and it's right now 5 o'clock on the clock and I say, meet me in 4 hours, I'm telling you to meet me at what time? What was that? 9, yeah, no trick questions here. So we can use the clock. Here I'm at 5. When I add 4, I go 1, 2, 3, 4. I'm at 9 o'clock. So 5 in my clock system, in my circular arithmetic system, 5 plus 4 is 9. And I don't think that's too big of a deal. That's not shocking anybody. Here's where things get a little bit more fun. Let's say I have 10 plus 4. Now the only elements I can come up with here are 1 through 12. So looking at my clock, when I do 10 plus 4, if it's 10 o'clock and I say meet me in 4 hours, what time are you going to meet me? 2. Right. So we go 10, 1, 2, but then my system, since it's circular, it resets 3, 4. So 10 plus 4 is equal to 2. It's not equal to 14. We are dealing with just the elements 1 through 12. Okay, so I'm going to write down a few more examples. And I just want you to take a moment, use the clock. It's sitting right there in front of you to count off. When you go and do your homework, they're going to give you a circular arithmetic system that just has 6 elements, and they'll give you a circle, and you're gonna count off just in the same way that we're doing here. So here's a few problems. So what would 8 plus 6 be? What would 5 plus 9 be? What would 3 plus 12 be? And then one more. Let's go. What would 7 plus 8 be? Okay, so just again, all it is, my only expectation, I'm not expecting you to be great with clocks or anything. My expectation is that you can use that circle to figure out the values. So the first one, if I start at 8 over here and then I add 6, then I'm going 1, 2, 3, 4, 5, 6. We should end up at 2. 8 plus 6 is 2, is how we would say that in this circular system. 5 plus 9, if I'm at 5, then I go 1, 2, 3, 4, 5, 6, 7, 8, 9. I did not do that intentionally, but I'm at 2 again. So I must have subconsciously 2 on the mind. Okay, 3 plus 12. When I start at 3, I go 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I end up back where I started. So 3 plus 12 is 3. And then last but not least, 7 plus 8. I hope this doesn't turn out to be 2. So 1, 2, 3, 4, 5, 6, 7, 8. Oh, I missed it by 1. It's 3. So there we go. So far, so good. Is everybody able to come up with those values? Okay, well, if we had a half hour, okay, and I wouldn't make you do this, and I said, let's fill in every possible combination of things we could add together, we get this table right below. And you're going to see a bunch of tables here. You're going to see tables on the sheet that we're going through today. You're going to see tables on the homework that define the mathematical system. So what this does is on the edges, you see the elements 1 through 12, okay? And then up here at the corner, this tells you the binary operation. So for us, the binary operation we recognize as addition. And now you can see all the results that you would possibly get in the table. Okay, and it would just be a matter of doing what we were just doing a moment ago. So for instance, I asked you to do 8 plus 6. So here's the 8 row, here's the 6 column, it's 2. That's just the value we get. I'm going to circle it just for kicks. And then 5 plus 9, the 5 row, and then the 9 column, again, we got 2. And then 3 plus 12, 3 plus 12 gave me 3. And then finally 7 plus 8. The reason I'm circling these is just so that you understand how this table is operating so that you could use it to figure out anything really quickly. Okay, everybody with me so far? Are you tracking with me? Okay, so now bringing this back on topic. We're on the idea of groups. So what I want to know is this system that we've been working is this clock 12 arithmetic system, or is this circular arithmetic system under addition a commutative group? Fantastic. Now we get to tap into our knowledge from last time. So you've already told me these things. So first thing, whoops, I need to slide this up a little bit. First thing, if I want to know if something's a group, what was the first characteristic? You already told me this. We're reviewing again. It's closed. So I want to know, is this closed? So closed meant that when I combine any two elements, if something's closed, what do I always get? You always get something in the set. You never get anything outside the set. So you might be saying, well, how do I know that, Perkster? Great question. Let's look inside here, okay, at all the elements. These are all the results that have been defined for my binary operation. As we scan through here, do we have anything in here that is not 1 through 12? Are there any zeros? Are there any 13s or 19s? Do you see anything off there? No. Okay, so is this closed? I'm going to say, yes, it is closed. And I'm going to give you a little reason so that you have it for your notes later so you know how we justified this. Is this closed? Yes, because all results are 1 through 12. And I'm just going to summarize 1 through 12. Is anyone not understanding why that's closed? Well, then let's call a timeout and let's go to the next page. Okay. Example 2. I've given 2 other examples of mathematical systems. So what I would like you to do real quick, these are 2 separate answers. I would like you to tell me if each of those are closed. It's a yes or no, closed or not closed for each of those. I'll give you 35 seconds to think about that. Shh, let everybody think. I appreciate your excitement though. So looking at the first mathematical system, I'm just asking you this question for later. What are the elements of the mathematical system? If I asked you to list the set of elements, you would tell me the elements are what? X, Y, and Z. That's what's on the side. The side are the elements, X, Y, and Z. Great. Is this mathematical system closed? Okay, this one is not closed. Why is this one not closed? Okay, there is a different result. That is not an X, Y, or Z, okay, because of the T right there, in case you didn't see it. So it's not closed because of the T. Does that make sense? That means that according to the way this mathematical system is defined, when whatever we would call this operation, I don't know what that symbol, how I would say it, but whenever I combine Z and Y, I get T. And that is not one of my 3 elements to my set. How about the second mathematical system? What are the elements of the set? A, B, C, just what's in the column in the top row. That's what defines the elements of the set. Is this one closed? Yes, it's closed. And the reason we can say it's closed is the results are all A, B, or C. Okay, there's no result of my operation that's anything different. So far, so good? We doing all right? All right, well then with your permission, I'm going to flip back to the front page. That's what it means for my finite mathematical system to be closed. So we're back to the question of, is my circular system a commutative group? So the second thing I need to know is what? Okay, that an identity exists. What does it mean for something to be an identity? Remind me. If I combine something with the identity, what do I always get? The thing, the same thing, right? So here's how you know if there's an identity exists. Okay. Look for a row or a column that repeats the original elements. So looking at this real quick, make sure if you heard what was said, that's fine. But if you didn't, I'm going to give you 15 seconds. I just want you to look at the table. And do you see an element that no matter what you combine it with, you get the thing back? And just a little hint, it was one of the examples I had you do at the top was the identity. So according to my clock system, what always produces the same element I started with? 12. Yes, notice up in the examples we did, 3 plus 12 is 3. And so when I look at the 12 column, or I can look at the 12 row, it doesn't matter. When I look at the 12 column, 1 plus 12 is 1, and then you got 2. This column here is the same as the set of elements. Does everyone see that? So does an identity exist for this? Yes, an identity exists. The identity is 12. Now, step 3. Now, I promise you that step 3, this will be the longest you will ever have to work on step 3. Okay, all the mathematical systems I give you after this will be smaller. Okay, and so step 3 won't take you as long for other problems. So I apologize in advance. It's not my intent. The whole reason I started with the clock is because we're kind of familiar with clocks, the 12-hour system that we enjoy. Okay, so what is the third thing I have to look for? Okay, every element has an inverse. And what that means is every element has another element you combine it with to make 12, right? And to make the identity. So what I'm going to do is I'm going to go up to the table, and what we're going to do together here is we are going to go through every element, and we're going to ask what is its inverse, because everyone has to have one. And so again, there's 12 elements we've got to go through. My apologies. So starting with 1. What 1 plus what gives me the inverse, or gives me the identity? Okay, 1 plus 11. Those two things are inverses. Okay, how about 2? 2 plus what? 10. Those are inverses. So I'm going through and I'm identifying every pair of inverses that I have according to the table. So then 3 and what? 4 and 5 and then 6 and 6, and I'm going to keep going because not every group we do will be commutative, meaning the same thing backwards and forwards. So I know you might be thinking the next couple steps are overkill, but it's unavoidable. So now I go 7. 7's inverse is 5, and then 8's inverse is 4, and then 9's inverse is 3, and then 10's inverse is 2. 10's inverse, there we go, I need to put a plus there, is 2, and 11's inverse is 1, and then last but not least, 12's inverse is 12 plus what gives you 12? There's no 0 in my set, so it's going to be 12 plus 12. And where I got that is I'm just going to circle where that came from. Let me use a different color on mine so that it's readily apparent. Where we got that is we just went through and we highlighted where are all the 12s. Every row and every column has a 12 in it. That's how you know that every element has an inverse. That will be the most laborious of the steps on this one. And like I said, pretty much everything else I give you is going to be a much smaller set, so you won't have to go through all 12 items and identify the inverse. It'll usually be 4 to 6 items that you're going to have to. Okay, so step 4. Now, step 4, the associative property is very difficult to prove, so I am never going to ask you to prove the associative property. This is what I will ask you to do. You are going to give me always an example of the associative property. This is just my way of making sure that you know what the associative property is. Okay, for a finite mathematical system, to verify the associative property, you would have to go through every sequence of elements, and that's way more torture than I'm into for myself even, so I would not have you do that. Okay, so here we go. I'm just going to make up an example. This is all I expect of you. So the associative property, remember, says if I have 4 plus 5 in parentheses, and then let's say plus 8, then what I want to know is that should be equal to 4 plus 5 plus 8. Okay, well, let's see if this is indeed true. And I'm just going to use my table to determine. So 4 plus 5, I mean, you know what this is, but I'm just showing you for future examples. 4 plus 5, 4 row, 5 column, that's 9. Then I'm going to go back up to the table. 9 plus 8, the 9 row and the 8 column is 5. So the result of the left side is 5 when I have the 4 plus 5 in parentheses. Let's go to the other side where I have 4 plus, in my parentheses, 5 plus 8. So let's see, 5 row and 8 column gives me 1. And then we know from basic arithmetic, 4 plus 1 is 5. So yes, the associative property indeed is true. So we're good. Or that's just an example. That doesn't prove it's true. It just proves that for that one instance, but that's where I'm giving you a pass on the associative property. And then last but not least, step 5, since I asked, is it a commutative group? You want to know, is it commutative? And here's how you can tell. This is why I like this is fun for me. When you have a table, this is the quick check to determine if it's commutative. What I'm going to do is I am going to draw a diagonal. I am going to start up here at this corner, this upper corner up here, and I'm going to draw the diagonal all the way down. So it's going to look like this. So 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10, 11, 11, 12, 12. I'm drawing that line through all of the sames. So 1, 1 is on the line, 2, 2 is on the line, 3, 3 is on the line, 4, 4 is on the line. So I've drawn that line through all the sames. Everybody with me? You see where I drew that line? So then you know it's commutative if what is the triangle above has the exact same things as the triangle below. So here, what does that mean? Why is that important? Well, here, 2 plus 1 is 3. 1 plus 2 is 3. So I've got the same thing below and above the diagonal. Same thing here. Below and above the diagonal is a 4. Here, I've got a pair of 5s and a pair of 5s. Same thing below and above the diagonal. Same thing here, a pair of 6s below, pair of 6s above. And I'm not going to bore you any more than I already have, but you can see as you go along the diagonal, you have the same thing stretching below and above the diagonal. And so that's how you know that this is commutative, and that's all you're going to tell me. It's commutative. How do you know? You have the same elements above and below the diagonal. So this has all the attributes of a commutative group. So the answer to the question is the clock 12 arithmetic system a commutative group? And the answer to that is yes, indeed it is. All right, so with that said, I meant to keep flipping over and doing examples, and alas, I forgot because I got excited. So here's what I would like you to do. We already did this for the closed example 3. I meant to flip over and say, okay, determine if the following systems have an identity. So I'm going to give you 45 seconds to look at those systems and determine yes or no, is there an identity element? And if there is, name it. So which chart are you looking at? Okay, so this is trying to help you understand that we can do operations. They can be defined without our traditional number symbols, right? So here on this one, W is the symbol for the binary operation. And so the elements of the set are A, B, C, and then this is the results when A and B and C are combined. So for instance, in case this is a great question, in case you're wondering what this means, I could do this. According to the table, if I take A, and right, our plus sign that we use, it's just an arbitrary symbol that somewhere along history, somebody picked and said, this symbol is going to mean addition. Right? So this W now defines the binary operation. So if I take A, whatever that means with B, A, W, B results in, so the A row, the B column results in B. That's what this table is telling you. So like the next one where it's all shapes, and I know that makes our brain cramp just a little bit. Okay, the top one, if I take the square and then I combine it with the binary operation, which is a circle with a line through it, so that's clever. If I take the square and I combine it with the triangle, what does that produce? Well, the square row and the triangle column produce that circle with a dot in the middle of it. Okay, so what these tables are doing for you is they are defining binary operations. What it's basically like when you were a kid and you learned your multiplications table, that's the multiplication table equivalent. Okay, it's defining all the results for you. And so what we're doing is so that your understanding of this is not linked to your understanding of numbers, right? So now we're defining like using letters and symbols, but it's the same process. So for the first one, that was a really great question. I'm so glad you asked it. Appreciate the bravery when somebody asks a question. So on the left one, is there, if you're looking at the columns or rows, it doesn't matter. I'm looking at this right here. I've got A, B, C in this column. Is there an element that produces A, B, C? In the same order. Because we're looking for an identity. Remember, identity means when I combine with this element, I get exactly what I started with. So is there an element that when I combine with A, I get A? Is it for that same element, when I combine with B, do I get B? And when I combine with C, do I get C? That's this column right here. When I combine A and C, I get A. When I combine B and C, I get B. When I combine C and C, I get C. So is there an identity for this one? The identity is C. So again, for the next one, I'm just looking at the columns. If you're a row person, you're looking at the top row. I'm looking at this column. I've got square, I've got circle with a dot, I've got triangle. Is there another column that is this exact same thing? Square, circle with a dot, triangle. No, there's one that looks perspective, right? When you start with the square here and you combine with this, you get the square. But then notice it fails when you do the circle with the dot and a circle with the dot, you get a triangle. It doesn't produce the same thing. So this one has no identity. There's no element that produces what you started with. Example 4. When we went through with our circular arithmetic, this was where we had to list them out. We went through and we listed every pair of items that gave us 12 on the previous thing. So what the problem here says is in each of these two tables, the identity is C. What we want to know is what's the inverse if one exists for every element. So what two elements? So as an example, what do I combine with A in order to get the identity of C? Okay, so it's kind of a goofy symbol. I apologize. I cut and pasted these out of a book. So I take A and I'm just going to do like a big cross looking thing instead of what they did. When I do A and the big cross looking thing with A, I get C. Okay, so those two things are inverses. So do that for B and C. What do you combine with B? What do you combine with C in order to get the identity? And I'll give you 15 seconds to look at that and do it. And then if you're feeling ambitious, look at the other one and go through every element. And what do you do to get C? What do I combine in this first table? What do I combine with B in order to get the identity C? Okay, B you combine with itself. So those two things are inverses. And then for C, what do I combine with C with in order to get C? Okay, yeah, so here are my results. And so A goes with A to get C, B goes with B to get C, C goes with C to get C. In that mathematical system, every element is its own inverse. So take a moment on the second table. I'll give you a little hint. One of the elements does not have an inverse. And what you're going to write is whatever element that is, element whatever does not have an inverse. Okay, so how about A? What do I combine with A in order to get the identity of C? There's no C in this row, right? A with A gives me A with B gives me A with C gives me A. So A has no inverse. What do I combine B with in order to get the identity of C? Yeah. B combined with B gives me C. And then finally, C combined with what gives me the identity of C. C again. Remember, the identity is defined as what two things do you combine together? Excuse me, the inverse is defined as what two things do you combine to get the identity? All right, one more. I told you the way when you're given a table to determine if something is commutative is to draw the diagonal down all the sames and then look and see if the triangle above is the same as the triangle below. So for both of these right here, I would like you to determine are they commutative or not commutative? So for the first one, I've drawn my diagonal down the sames. Okay, so what I mean by the sames is when I combine P and P, I get L. A and A gives me L. L and L gives me P. So those are the sames. So I want to know now, is this commutative? Do I have the same thing in the triangle above and the same thing in the triangle below? Okay, so I've got P and P right here. Those are the same. So far, so good. I've got A and A here. Those are the same. But where it fails is I've got L below the diagonal. I've got A above the diagonal. So that's how I know that this one is not commutative. So I'll give you a moment to look at the second one in case you were confounded, because this is difficult stuff. To look at the second one and determine, is it commutative or not? So I've drawn the diagonal. Do I have the same thing above and below the diagonal on this one? Yes. Yes, in case you can't see it, above and below, I've got W's right here. Those are the same. I've got A's right here above and below the diagonal. Those are the same. And then I've got circles with X's in it. Those are the same. So this one is a commutative system. And the way I know is I have the same results above and below the diagonal. All right, so you've seen all my tricks. Okay, you've seen everything that I possibly want to tell you right now. So how we're going to spend the rest of our time and the rest of this sheet is just doing some examples to get used to doing this very funky thing that we're looking at. So here's the next one. We're going to go step by step here together, just in case. So consider the following mathematical system. So the operating symbol is the, that's going to be something you have to identify. I'm just too excited. So here's what I want you to do. The A and the B part. I want you to first do the A and the B part to this, list the elements of the system, and then identify the symbol for the binary operation. Okay, what are the elements of this system? Just the thing on that initial column and that top top row. Don't look at the body of the table for the elements of the system. Those are the results. So we've got 2, 4, 6, and 8. Those are the elements of the system. Fantastic. How about the binary operation? What is the binary operation? Yeah, it's the copyright symbol. It's the C with the circle around it. Perfect. So now we want to know, and what you're going to show me is we're going to go through and we're going to go one thing at a time, and we're going to determine, is this a commutative group? And my instruction says just what I mentioned earlier. For the associative property, just illustrate with an example. Okay, you can always assume something's associative unless I tell you it's not. Okay, because that again is very hard to prove. So first thing, determine, is this closed? I'm going to give you 20 seconds to make your conclusion. Is this closed? And remember, when we are determining if something's a commutative group, the second we come across something that it fails, we can stop. We are done. We can say no. All right, is this closed? Yes or no? Yes. How do you know it's closed? Yes, all of my results in the body of the table are 2s, 4s, 6s, and 8s. So the results are all 2, 4, 6, 8. There's nothing else. All right, so then we've got to go to step 2. Step 2, I'm going to give you 30 seconds. See if you can identify, is there an identity? If there's an identity, tell me what it is. If there's not, write no identity, and we'll be done with the problem. All right, so I'm looking at the column. If you're looking at the row, you'll come to the exact same conclusion. My elements are listed as 2, 4, 6, 8. Is there an element that produces another column 2, 4, 6, 8? What is that? 6. Yes, here it is right here. 2, 4, 6, 8. If you're looking at the rows, 2, 4, 6, 8. So the identity is 6. The third thing you're going to do is, since there's an identity, we're going to see, does every element have an inverse? So for 2, 4, 6, and 8, identify if there is an inverse element. All right, so remember, how do you know you found its inverse? If when you combine it, it gives you the identity, which in this case is 6. So is there something that I combine with 2 in order to produce 6? Yeah, 2. Okay, 2 combined with 2 gives me 6. Those are inverses. Great. Is there something I combine with 4 to give me 6? 8. Yes, 4 combined with 8 gives me 6. So far, so good. Is there something I combine with 6 to give me 6? 6. And then last but not least, is there something I combine with 8? 8 and 4 give me 6. So every element has an inverse. Every element has something that I combine with it to give me the identity. So we are going to keep going. Okay, so step 4. Okay, step 4 is the associative property step. So what I would like you to do is to make up an associative property and verify using the table that it holds. You know what, let's all do the same one on this first one, just to make sure we're all doing the same thing now that I'm thinking about it. So this is arbitrary. I've not done this yet. So let's do 2 plus 6 in parentheses plus 8. And I want to know, or I want you to verify, is that equal to 2 plus 6 plus 8? Okay, so I'm just making up an example, and now you're going to use the table to verify the associative property holds. All right, so here we go, using the table, 2 plus 6, I've got 2, I go over to the 6 column, 2 combined with 6 gives me 2. I used pluses here for some reason, just because I'm trained. These should all be copyright symbols. My bad, bad Professor Perkins. Sorry about that. And then so I'll combine that with 8. So now 2 combined with 8, I'm in the 2 row over to the 8 column, and that is going to be 4. On the other side, I start with the parentheses. So 6 combined with 8, so I'm in the 6 row. I go over to the 8 column, so 6 combined with 8 gives me 8. And then 2 combined with 8, 2 combined with 8 gives me 4. And notice the associative property seems to hold because we've got the same thing both ways. So last but not least, since we're asked if it's a commutative group, is you are going to determine, is this commutative, yes or no? So I'll give you 30 seconds to draw your diagonal and determine if it's commutative. Okay, so I've drawn my diagonal. I'm looking, so above and below the diagonal, I have 8s, I've got 2s, I've got 4s here and 4s here, 6s and 8s. It looks like I have the same exact thing above and below the diagonal. So this is commutative. Keep spelling commutative wrong. And it's commutative because it's the same along the diagonal, as we've said before. So is this a commutative group? Yes, it is. So I'll just write a little yes right there. All right, so I'm going to give you about 5 or 6 minutes. Example 7 is the same sort of thing. I don't know. I haven't done these examples, so I'm learning as you learn. Do the A part and the B part, and then determine if it is a commutative group. I'm going to get started. Keep working if you're working. If you got a question, check your answers with mine, all that good stuff. So here we go. Listing the elements. I've got 3, 5, 8, 4. Those 4 things are the elements. The binary operation, the symbol for it is the letter T. So now we're going to determine if this finite system is a commutative group. So the first thing, is it closed? Well, all I see are 3, 5s, 8s, and 4s here, so it's closed. We only get 3, 5, 8, and 4. Second thing is there an identity? Is there an element that always produces what you start with? What's the answer to that? Yeah, 4. My first column is 3, 5, 8, 4. Right here, 3, 5, 8, 4. So the identity is 4. So step 3 then is I'm going to determine what is the inverse for each element. And if each element does not have an inverse, you're done. This is not a commutative group. So 3, when I combine with what, produces 4? Yep, 3 combined with 8 equals 4. And then 5 combined with what produces 4? 5 combined with itself. Yep, and then 8 combined with 3. And then last but not least, 4 combined with itself. So every element has an inverse, so we can continue on. The fourth thing is give me an example of the associative property. So I'm assuming we're all probably going to have different examples. So your example looks something like this. So if I did something like this, let's say 5 plus 5 plus 8, I want to know, is that equal to 5 plus 5 plus 8? So whatever 3 things, I used plus again, I'm sorry, it's T. So whatever 3 elements you used on the left, you used the same 3 elements on the right in the same exact order, just the parentheses in a different place. So according to the table, when I combine 5 and 5, I get 4. And then when I combine 4 and 8, I get 8. On the other side, 5 combined with 8 is 3. And then 5 combined with 3 is 8. So I got the same thing. The associative property seems to hold. Last but not least is this commutative. So I draw the diagonal just right there. Do I have the same thing above and below the diagonal? Looks like it. So this is commutative. And I'm going to leave it at that. Okay, just for time's sake, I didn't do a great job with all the examples. We're going to skip example 8. If you want to verify, I will do a video of this later for you, and I'll post it on Canvas. So if you want to do another practice problem, that's great. But we're just going to skip down to example 9, a little bit of a smaller system. So do the same thing. All right, so I'm just going to get started. If you're working, keep working. So on my table, the elements are 4, 5, and L. So you can see them right there. The binary operations define the B and $sign. So we're going to determine if it is a commutative group. So the first thing is it closed. I only see 4, 5s, and L's in the table, so it's closed. Okay, the results are all 4s, 5s, and L's. The second thing, is there an identity? What's the identity on this? Okay, so then the third thing is I'm going to go through each element. I'm going to determine if there is something that produces L for each of that. So when I do $4 with what do I get L? 5. And then when I do $5, 4 is going to give me L. And then L, dollar with L gives me L. Okay, so 4 and 5 gives me, there's my L right there. 5 and 4, there's my L right there. And then L and L, there's my L right there. The fourth thing is you picked an example of the associative property. Again, you have lots of latitude here. So I'm just going to do L plus 5 plus 4. And I'm going to verify that this is going to be equal to L plus 5 plus 4. So L, and the first one, I used plus again. I've done that every time. Bad, Professor Perkins. So $5 is L. And L dollar itself is L. And then we're verifying. So L $5 is 5. And then $5 4 is L. So we get the same thing. We've verified the associative property. Last thing is this commutative. So I draw the diagonal. And yes, I have the same thing above and below. So it's commutative. All right, last problem for the day. Last page. So this mathematical system is, they are telling you, or I am telling you, that it is a group and it's not commutative, which is very hard to make a table that is not commutative and is also a group. So you're going to do 2 quick things. I'm going to give you about 4 or 5 minutes to do it. First thing you're going to do is you're just going to pick an example to demonstrate that this is not commutative. And then verify the other 4 properties that tell you that this system is a group. And that will end us for the day. So counter examples abound on showing that this is not commutative. So for instance, Here's one that's right at the top. You can do B and then circle with the wave. You can do B, circle with the wave A. So B, circle with the wave A gives you D. And then if you reverse it, A, circle with the wave B, that gives you C. So you get a different result depending on what order you do. I'll do another one just to show you that there's plenty of options. So if I do B, circle with the wave D. So B, circle with the wave D is going to give me a result of A. Then if I reverse it, D, circle with the wave B. So D, circle with the wave B gives me E. Okay, and I think it would actually be harder to find one that was commutative, a pair that was commutative, than to find pairs that aren't. So whatever you pick. So that's the essence of it. You're picking two elements and you're just changing their order to see that you don't get the same thing either way. So then the other one, I've already told you that this is a group in the problem. So all you're going to do is the 4 steps to show that. So the first thing, you're going to verify it's closed, and it is closed. All the results, I was looking while you were doing the problem, it's closed. All results are A through F. The second thing is, what's the identity? The identity looks like it's going to be F. Is there my first column of elements, A, B, C, D, E, F? My right here, all these results, A, B, C, D, E, F. So I get exactly what I started with. The third thing is I have to identify now a inverse for each of those elements. So I need to know for all 6 elements, what's the inverse? So let me just write first. A, circle the wave. B, circle the wave. Let's go over here. C with the circle the wave. D, circle the wave. E, circle the wave. And F, circle the wave. So far I haven't written any pluses on this particular problem. Okay, so I want to know each time what one gives me an F. So for A, I combine it with E to produce F. So it has an inverse, so far so good. B, I combine with itself to get F, so 2 for 2. C combined with itself gives me F. D combined with D, it's not super interesting. E combined with A, and then probably F with itself. There we go. Last thing is you're just going to verify the associative property. So again, we all probably have an example that looks a little different. So I'm going to do C, circle the wave F, circle the wave E. And I'm going to verify that that's equal to C, circle the wave F, circle the wave E. And I'm just going to use the table to do it. So C combined with F, when I come up here, C combined with F produces C. And now C combined with E, I go back up here, C combined with E produces D. All right, on the other side, I'm going to start with F combined with E. That produced E. And then C combined with E, C combined with E is D. I got the same thing. I have verified the associative property. So if you had trouble verifying, then stop by when we're done and let's just double check. But whatever you picked, it should work out to be the same either way you do it.